Okay, good morning, ladies and gentlemen. This is Professor David J. De Los Reyes. My topic for this morning will be a continuation of my long video format topic, DC circuit, and I am now on lesson number 29. So the topic for this morning will be a long video format topic in direct current circuit, lesson number 29. Okay, let's proceed. The title of the topic for this morning will be a long video format topic, direct current circuit, lesson number 29. And the title of the topic will be, this is an application of the concept under DC circuit. So the title will be Y to Delta Transformation Problem. So for this morning, I will be discussing a problem that involves the so-called Y to Delta transformation, meaning we needed the concept on the Y to Delta transformation to solve the given problem, because without knowing it, we could not solve the problem. Okay, let's proceed. We are given the given figure here. The values are given. Okay, this will be 24. This is 1 ohm. This is 2 ohms, 5 ohms, 3 ohms, 4 ohms. The resistances in the Y configuration is with the value 6, 7, and 8. And we are given 3 points. I place the designation of the points on the circuit. This will be point A or junction A, junction B, and junction C. I place the specification on the junctions because when we try to simplify the circuit, we must have to identify where we get the values of the resistances. The problem here is find capital letter I with the subscript T, meaning the total current. So with the given circuit, the problem is asking what will be the value of the total current. Okay. Total current, it will just be simply, if we try to solve for the total current, it will be the total applied voltage divided by the total single equivalent resistance of all of these. Okay, we will be solving the single equivalent of all of these, and the problem is it's a complicated circuit. Why complicated? Because on the portion at the back there was a Y configuration resistances which are resistances which are connected in the so-called Y configuration. This 6 here, 7 and 8 is in the Y configuration. Okay? So to simplify this portion here, we must have to convert this Y here to its equivalent in delta. That's why the title of the topic for this morning is Y to Delta Transformation Problem. Because without knowing the concept of Y to Delta transformation, we could not compute for the single equivalent of all of this. Because if we try to get our multitester here, okay, we could measure the total resistance that is on the actual thing. But how could we solve that one on the board? So if we try to take the single equivalent resistance across this terminal here, the single equivalent of all of this, we must have to start on the right hand side. We simplify each part of the circuit going from right to left, from the complicated thing to the simplest one. So we will be starting on the right side. So to compute for the total current here, it will just be simply the total applied voltage divided by the total single equivalent. Okay? But the problem here is that the computation of capital letter R with the subscript total, meaning the total resistance, it's a complicated thing. Okay, let's proceed with the solution. So the proper solution of this one is actually, if we try to observe the right hand side, this was the complicated part, right? Because if the Y connection at the middle is missing, it's a simple problem, but the problem is there was a resistances with the configuration Y inserted across points A, B, and C, and the values are actually 6, 7, and 8. So to simplify this portion here, we must have to use our knowledge of the Y to delta transformation. So I brought out this portion here. This across terminals A, B, and C, it will be this. Right? This is terminal A, terminal B, terminal C. This is 6, 7, 8. So we will be solving for the value RAB here. This is RBC. Then this is R sub AC. Okay, we must have to convert this Y here to its equivalent in delta. That's why our topic for this morning is Y to delta transformation problem. Okay, I will try to check my camera. Okay, my camera is fine. So it seems I disconnected this portion here. Right? This portion. I just took this one, it is this. So to compute for RAB, RBC, and REC, I place it here. Convert the Y to delta at points ABC. So RAB, RBC, and R sub AC, if we try to recall the formula and how to compute for the conversion from Y to delta, this is the formula. It will be the individual product, 6 times 7 plus 7 times 8 plus 8 times 6. If we are taking these values here, take the product of 6 times 7, 7 times 8, and 8 times 6. That will be the complete denominator, numerator, divided by. If we try to compute for RAB, the resulting numerator will be 8 ohms. RAB, the opposite of this one on the Y configuration is actually 8 ohms. So this is 8. And if we try to compute for RAB, that will be 18.25 ohms. Okay, so we are now given the value of this one. For the value RBC, it will still be same numerator, but if we try to compute for RBC, the denominator should be the opposite resistance considering the Y. So if we try to compute for RBC, the opposite of this one on Y is actually 6 ohms. So this is over 6. And what will come out is 24.33. For R sub AC, meaning the resistance equivalent between A and C, okay, it will still be same numerator, but if we try to compute for RAC, its opposite resistance considering the Y is actually 7. So the numerator here is 7. So this is all over 7. And what will come out is 20.85 ohms. So after the conversion from Y to delta, it seems this 6 ohms here is gone, this 7 ohms is gone, and this 8 ohms is gone. Right? We removed them already because we got already the delta equivalent. And we will bring back this delta equivalent to the circuit. Okay? This 2 ohms here was originally there. But according to our delta solution, the points, considering points A and B, we computed what is RAB is 18.25. This is 18.25. 2 ohms is this one. Okay. For R sub BC, we computed 24.33. So considering points B and C, this is 24.33. This is actually the delta equivalent, the one we computed. And considering points A and C, the computed resistance is 20.85, so this is 20.85. Okay, so still this is 5 ohms, right? This one is still 3 ohms. So that's the equivalent now after the conversion from Y to delta. And if you try to notice it, these 2 ohms and 18.25 is in parallel. This 5 ohm and 24.33 is also in parallel. And this 20.85 and 3 ohms is also in parallel. So to compress the circuit now to a more simplified form, we will take the single equivalent of this one, the single equivalent of this one, and the single equivalent of this one. So I designated the single equivalent of this 2 and 18.25 as X. Okay, the single equivalent. The single equivalent of this one is 1. The single equivalent of 24.33 and 5 will be Z. So I place this one as the single equivalent Y, single equivalent X, and single equivalent Z. And the three things are actually in parallel. And if we try to compute for the single equivalent of 2 resistances in parallel, it will be the product all over the sum. So considering this X here, it will be the product 2 times 18.25 all over the sum. And what will come out will be 1.822 ohms. So this is 1.822, right? Considering Y, it will be the product 3 times 20.85 all over the sum. And what will come out is 2.622 ohms. So this is 2.622 ohms. And considering Z, it will be the product 5 times 24.33 all over the sum. And that will be 4.17 ohms. So this is 4.147 ohms. Right? Okay? Again, if we try to simplify further the circuit, we could say that this X and Z is in series. So we will try to take the compressed equivalent of this one. I place it here, that will be X plus A. And it is in parallel with Y. In what is Y? 2.622. So this is 2.622. Okay? X plus A will be 5.949. Right? And again, if we try to take the single equivalent, if you notice it, as we move further, the resulting circuit will be less complicated. Because we've gone from the complicated to the less complicated, and the final portion will just be simply a series circuit. So after computing for this portion here, these two here is in parallel. So if we try to take the single equivalent of this, they are in parallel, right? Product all over the sum. What will come out will be 1.822 ohms. So this is 1.822. This is 1 ohm. This is 4 ohms. And if you try to notice it, after the successive, what we call the simplification of the circuit by using our knowledge of the Y to delta and the concept of parallel concept, the resulting circuit now will just be simply a series circuit. 1 ohm will be in series with the single equivalent of all of this. And the single equivalent is actually 1.822. Right? And this will be in series with this 4 ohm here. Okay? So this is an AC matter now. We are given 3 resistances in series. The total resistance will be just be simply the summation. So this is 1 plus 4 plus this. The single equivalent of this complicated thing here. 1.82. And what will come out will be 6.82 ohms. So meaning to say, the single equivalent of all of this will be 6.82 ohms. Okay? So if we now try to compute for the total current, it will just be simply the total applied voltage divided by the single equivalent after the successive simplification of the resistance A. And that is 6.82. So the total current now, Ohm's law, it will be voltage over resistance. Total current now will be 24 over 6.82, and what will come out will be 3.52 amperes. Okay, that's it, guys. Okay, I will try to check again my camera. It's still fine. So, the key to the solution of the problem here is by using our knowledge of the so-called Y to delta transformation, plus our knowledge on the simplification of a parallel circuit. We will be going from the complicated to the least complicated until the final part on the computation of R total. It will just be simply a series set. Okay? And Ohm's law will be the voltage is product of current times resistance, therefore current will be voltage over R. And what comes out for the total current? With this complicated circuit here. I say complicated because this Y configuration was inserted. If without the Y configuration, it will just be simply a simple circuit. But the introduction of the 6, 7, and 8 at points A, B, and C, this portion here could not be solved without using our knowledge of the so-called Y to delta transformation. Okay, that's it, guys. So for those of you who would like to watch my channel is at youtube.com/@Prof. My channel comprises of long video format topics. For those of you who have not watched my channel comprises of long video format topics. I have completed already the differential calculus, integral, differential equation, advanced math, DC circuit, AC machines, algebra, and analytic geometry. It's a complete syllabus. It's a good thing for those who would like to take up engineering, because if you try to watch my channel, okay, you could learn something from it. It's a good preparation for taking up an engineering course. For my short videos, it comprises of electronics, because I know hands-on electronics. I could troubleshoot to the component level. I could, assemble a circuit, actual circuit, and some other things. That's the component of my short videos. But the main concentration of my channel is actually on the long form videos. Those 10 subjects, it's a complete syllabus already. I think that's what I can say for this morning. This is Professor David J. De Los Rios. What I have discussed is DC circuit lesson number 29, Y to delta transformation problem. Good morning from Los Angeles.